Okay, yeah, let's crack on. So, today is going to be a bit of a split revision class between the Unit 1 and 2 and Unit 3 and 4 stuff. So, let's crack on with that. So, one of the topics that I found comes up occasionally is this idea of maximal domains, or even just domain and range in general. How do we handle those things? And it makes a decent amount of sense why this comes up so often as a bit of an issue, because simply put, there's a whole bunch of different functions and they all have different rules as to how they work. So to make things maybe not necessarily simple, but all self-contained in the same sort of document, what I've done is I've put a full list of all the functions, all the function types that you come across into the same document. This is under the Functions and Relations tab around, I think it's Fundamentals of Functions and Relations. Talks about the domain and range and all that sort of stuff, specifically in the context of all of these function types. So that'll be like maybe the first half of the lesson. Then we'll move on to the applications of integration, where, yeah, we'll probably touch on those from the ground up, because I'm pretty sure some of you haven't had a look at this just yet. Cool, so let's crack on. So what you'll notice is a decent amount of these have the same maximal domain of all real numbers. This is because when we think about domains of functions, what we're effectively trying to figure out is what are all the possible x values that I can put in a function, right, without breaking the math. For stuff like linear and polynomials, there is no real x value that you could put in there that would break how you do the math. It's only when you get to more complicated graphs and functions where these rules start to break. Like, for instance, the logarithm, right? The logarithm is such a function where the brackets, the inside of the logarithm, must be greater than 0 at all times. The logarithm ever having a 0 or negative number in the brackets is considered invalid because it would either be undefined or would have a non-real result. Similar to stuff like tan, where tan has asymptotes, has those vertical asymptotes. Anytime you have a vertical asymptote, that by definition is one x value that cannot exist on the graph, which is why for the maximal domain of tan, we're going to exclude those asymptotes. Exact same thing for the hyperbola and the truncus. Again, those both have vertical asymptotes, specifically 1. And so you're essentially excluding that spot where you are dividing by 0, because any divide by 0 is going to give you that vertical asymptote. Roots are going to be similar to logarithms, although there's going to be a bit of nuance with the root, depending on if you have an even or an odd one. By far the most common that you'll come across is going to be the square root, so the second root of a function, and that would be considered an even root. Any even root that you have, the inside of that root needs to be either positive or 0. You can never have the square root of a negative number or the fourth root of a negative number. Not so true of the odd roots, however. Those are your third root, your fifth root, so on and so forth. That's because you now have a mismatch or an odd number of times that you're multiplying your number. Like, for instance, when you do like -1 times -1, you go back to being positive. But if you do it 3 times, you do actually get back to being negative. So in summary, odd roots can actually have a negative number associated with them, which is why there's no restrictions on that one. So the only examples I'll give will be the cases where the domain isn't just going to by default be all real numbers. So let's have a look. Logarithms. As we said, the rule for that one is that the inside of the logarithm must always be positive. So in other words, take whatever that is, solve the inequality, make it positive. In most cases, this will just be linear, so you can just do a very basic linear equation or linear inequality solve, and you'll get your domain. If it's anything more complicated, like a quadratic, for instance, your best bet is to start sketching those. Pretty much any polynomial that could go in here, or any other type of function for that matter, you'll typically be best served by sketching that function first, and then looking where is it above 0, where is it below 0, and so on and so forth. That's it for logarithms so far. Any questions about how that one's worked? Easy. For Tan functions. Now, depending on how your school has structured your SAC, circular functions may be something um, after SAC 1. And so, also after the calculus SAC, I should say. So you may or may not be doing this as part of the first one, at least for 3 and 4. Unit 1 and 2, this will be with your other circular function stuff, of course. So if you're not too familiar with the circular function stuff, that's okay. You don't need it for your SAC until then. But as we discussed, so tan is this type of graph where it has these vertical asymptotes. I'll get an example up now. Let me find one of those. Circular functions, tan. So tan looks like that. Kind of cubic-like in its overall shape, but it's also got those asymptotes that are separating each of those cubic-like shapes. Those asymptotes, oddly enough, occur because of a divide by zero error. But when you think about tan, like where's there a divide by zero? Well, it's because tan, by definition, is sine divided by cos. So as soon as you have division, there's the possibility that that division might go to zero. So in other words, we're now trying to solve where does this go to zero. If you haven't done circular function solving yet, don't worry too much. Just understand the concept that whenever you're dividing, whenever you have functions that are dividing by themselves or other things, there's always the possibility that that thing goes to zero. And dividing by zero is not possible or undefined as far as method is concerned, which is why we have those asymptotes. Thus, is excluded from our domain. For those who have done circular functions before, all we're doing is basically getting the general solution to this circular function. We want to figure out where does cos equal 0, which is going to be at the plus minus pi over 2s, or the pi over 2 and 3 pi over 2 spots on the unit circle, and then every other revolution from there. That's what that 2 pi n there is for. From there, we're just rearranging for x and then condensing things down as neatly as we possibly can. As a reminder, this is where we have the asymptotes, which means it's what we're excluding from the domain. So it's going to be x is an element of all real, excluding this. Just keep in mind that when you do introduce new variables, you want to make sure that you're actually giving them some sort of definition or some sort of restriction on it to make it more clear what n actually is, which in this case is going to be an integer. Anyone need this more clarified? Really more so if you've already had a look at circular functions. We can dive into that a bit more. Sweet. Okay. Next up, hyperbola. The exact same scenario. We've got something divided by something else. Division by 0 is now possible. So the maximal domain of the hyperbola is again going to be everywhere where the denominator does not go to 0. So again, just take that denominator, make it equal 0, figure out where it equals 0, which in this case is going to be at x equals -3, which is why our maximal domain is going to be all real excluding -3. Truncus, again, exact same thing. It doesn't matter what's on the bottom of that denominator. Could be a sine, could be a cos, could be a logarithm, could be a whatever. Whatever's on there, if you have a divide by something, divide by function, if it could go to 0, that needs to be excluded from your domain. So again, we're just going to grab the full denominator, make it equal 0, and then figure out where does that go to 0, and exclude that from our maximal domain. All about those. Truncus, hyperbola, tan, they all have the exact same approach to how you solve them. Sweet. Finally, the even roots. So this is going to be very similar to the logarithm, where instead of having to always be positive, in this case, 0 is also valid as well. You can have the square root of 0, because 0 times 0 gets you 0. Whereas with the logarithm, there's a bit more nuance behind like why you can't have 0. It's got to do with the fact of it, when you convert to the equivalent exponential equation for it, 0 is not a valid option for it. It's undefined. But anyway, for the root, we don't have to worry about that. It's just going to be greater than or equal to 0. So again, whatever this is, whether it's linear, quadratic, a logarithm, or whatever in there, grab that whole thing, make it greater than or equal to 0, and then solve that inequality. If it's linear, you can just rearrange that nice and easy. If it's anything more complicated, sketch that graph first, and then see where is it above the x-axis. In fact, I've said that a couple of times. So what I'll do is I'll show you exactly what I mean by the sketching approach for inequalities. So is it going to be quadratics, maybe? Where did I put this? Polynomial inequalities, yes. So what do I mean? It's like when you have something like this and you're rearranging and trying to solve your inequality, you can't really just solve this the same way you solve normal quadratics, where well, you kind of can, but it's quite an ordeal. Like if you try to factorize this and try to figure out where is this less than 0, you can't really do like a null factor law thing. You're kind of doing sign analysis, which we could go into detail on, but a much easier approach is to just use a skill that you already have, which is sketching a quadratic. So basically, first step is make sure every term is on the same side, and you're doing inequalities around 0, whether it's less than 0, whether it's greater than 0, whatever. In this case, you're always doing the greater than or equal to 0 anyway, so you won't have to worry about the rearranging side of things. Once you have it all on the same side, sketch whatever that thing is. In this case, it's a quadratic. You can sketch this however you like. In this case, you don't really have a factorizing option available. This one was a quadratic formula approach here. So use a quadratic formula, get your x-intercepts. Your y-intercepts is a little bit irrelevant, but we'll see why in a bit. It's more so going to be x-intercepts and turning point. So as long as you can get that overall shape going, the way you then take it from here is if you're looking for function greater than 0, you're looking for where is it above the x-axis. If you're looking for a function less than 0, you're looking for where it's below the x-axis. In the example that we just had, that was our inequality, right? Function less than 0. So we're looking at this bottom blue bit here. So when solving that inequality, we just want to say, what are all the x values where this function is greater than 0? Less than 0, sorry. Which is going to be between these two spots here. All right, this is exactly 0, this is exactly 0. Everything in between is less than 0. So final answer, x is an element of that, comma, that, non-inclusive, because we want less than. If we had a similar thing over here where it was greater than or equal to, then you would use the square brackets on those instead. That's a neat little thing that you can do when you're dealing with inequalities of non-linear things, which does come up. So it's good to understand that you can always just sketch them, which every function that you come across, you'll be taught how to sketch anyway. So you're not really learning any new skills beyond how to interpret what you've just sketched already. So it's pretty lightweight as far as adding it to your repertoire of how to handle these questions. That being said, it is a somewhat new concept, so are there any questions or clarifications for how this approach to inequalities works? Sweet. The last kind of issue that you might come across, almost certainly in the exam, is going to be when you have a combination of functions to deal with instead. So, as we can see here, you're not taught how to handle this function. Like, we don't know how to sketch this. You could, like, work around it and plot out some points and get an idea of what it looks like, but there's no one rule for this thing. But it is made up of functions that we do know how to handle. It's made up of the square root, it's made up of the logarithm, and there's a sneaky sort of third little thing going on there, which is that it's being divided. So anytime you see that division symbol or fraction symbol, always got to watch out for the possibility of a divide by 0. When you have such a combination of functions, all you're going to do is evaluate each of them individually and then essentially combine all the results together. Because if this function is invalid, then the entire thing is invalid. If this function on the bottom is invalid, the entire thing is invalid, right? It only takes one thing to break before it all breaks. So we're just going to do exactly that. Go line by line, function by function. As we discussed before, the root can only be positive or 0. So in other words, grab whatever's on the inside, make it greater than or equal to 0. In most cases, when it's a combination of things, they're not going to make that too complicated. So they usually will give you linear there. But again, if they give you anything more complicated than that, you can use the procedure that we just mentioned earlier with the whole, the graphing thing. That's going to give us x greater than or equal to -2. So in other words, this part of the function is valid so long as x is greater than or equal to -2. Now for the logarithm part, very similar, but instead of it being greater than or equal to, it's just greater than. 0 is a non-inclusive thing for the logarithm in particular. As a further nuance, for those who are doing more than, for those who have had a look at logarithms already, that's also true of non-natural logarithms. If you have a different base, for instance, it's for the same reason. But yeah, again, just take whatever's on the inside of this, make it greater than 0. So in this case, that part of the function is only valid so long as x is greater than 1. So we can already see a bit of a disconnect here, right? This one's valid for more than this one is. So if I had, for instance, x equals -2, yeah, this part's cool, but this part is not. Last up, we're going to handle that divide by 0 possibility. And I do say possibility because sometimes that bottom function might not ever be able to go to 0, but it is something you have to validate when you do this sort of thing. So because we're dividing by the logarithm is the thing at risk of going to 0. So we're going to try and solve. Where does it go to 0? If it goes to 0. So as a quick recap for how we handle logarithm solves, it's going to be flipping to the exponential form. And again, if you haven't looked at logarithms yet, it's not going to be super relevant for you, but for those who have, as a quick reminder, the base of the logarithm becomes the base of the exponential. Whatever is the equal sign will go up the top here, and whatever's on the inside of the logarithm goes on the other side of that equal sign. E to the 0 is just 1, add 1 to both sides, you're going to get the x equals 2. So this x equals 2 is going to be something that causes the bottom to go to 0. So in other words, the divide is perfectly fine so long as x is not 2. Now, at this stage, we've basically just gone function by function and that division and gotten our initial results. Is there anything about those that need clarification so far? Cool. So how do we put it all together? My personal favorite is just using a number line. So yes, you could look at these individually and just rationalize what's it going to be. But if you just literally put it on a number line and then just look where are they both true. So here's the x greater than or equal to -2. Here's our x greater than 1. Remember, this is all in terms of what is good for the function versus what is bad for the function. So we look at the intersection. Where is both of these functions okay? As we can see, the whole thing is going to condense down to exactly just x greater than 1. All we're going to watch out for is that x equals 2 thing that still was lingering there. You could put this as a dot on your number line if you wanted to. It's like a little open dot, but I don't know. I just neglected not to because reasons. You can do it if you want. So whatever you do basically to make sure you don't lose track of it, essentially. So we have the inequality that we wanted to have, which is the x greater than 1. So x is an element of 1 to infinity, and then we're excluding that one issue with it. Inspire has an inbuilt function to do this for you. So unfortunately, if you have a Casio, you don't get to use this. But if you search the book button on your TI Inspire and click D, I'm pretty sure it's one of the first options there actually. Let's have a look. So if we go to the handwritten section, there's the book button right underneath the delete. We hit D. Nah, okay, it's not the first one, but it's going to get there pretty quickly. Which is that right there. You click that, you put in the syntax exactly as I've written. So basically it's just function, comma, x. Might as well do that just to show you. Square root x plus 2 over natural log x take 1. And then all you're going to do, just like the solve, you're going to do your comma x. And once again, we're going to see that whole 1 to infinity, excluding 2. Just making sure that when you put that in as your final answer, yeah, you'll get the mark for that. But if you're on the edge of a study score increase when you're doing your actual SAC or exam, mainly the exam, it'll be good to use the actual set notation that I've highlighted in the green on the notes themselves. That's going to be the main part that's challenging about that chapter, which that chapter is chapter 5 in the unit 1 and 2 bit. So let me know any questions about that, or should we dive into some examples from chapter 5?
Could we do some examples?
Yeah, let's do it. So where's that? It's going to be the 5D, implied domain or maximal domain. Oh yeah, the other thing I didn't talk about was range, but that's because range is something that comes second nature to when you finally have your domain. So as soon as you know the domain of the function, literally all you're doing is sketching whatever that function was over that domain. So for instance, if your domain was maximal, you would sketch the full thing. If the domain has a cutoff like here or here, you would just stop drawing a graph there and there. And then literally all you're doing is looking at the bottom, looking at the top, and then just saying whatever those values are. That gets you your range. Okay. So this was chapter 5D 183. Let's see. Let's go 4. So some of them are going to be quite basic. I don't know if this gets any... It gets kind of more complicated sometimes with what they're putting inside of things. Yeah. Let's start simple with 4A. Okay. So 4A, we got f of x is equal to square root x take 4. I'll have the little cheat sheet up for what's what. Oh, I didn't have that in the summary. Oh, shit. I guess it's up here then instead. And I'll grab a screen cap of that as well. So that'll be dot point 8, right? The even root that we're dealing with. All right, maximal domain. What are we worried about for this function? What could possibly break it? I'll even scroll down to the example that's relevant for it. It'll be example 5, right? It's a very similar graph. Square root of a function. What's going on there? How do we do it? I think I saw you come off mute, but nothing came through. Sorry, Nihal. Audio issues. Uh-oh. Still nothing. Oh, maybe like, yeah, here we go. That's better.
Yep. So for square root, it's you have to get the brackets. I mean, whatever's inside the square root to be greater than or equal to 0.
Exactly right. So
So x minus 4 greater than or equal to 0.
exactly right. Yeah. X take 4 greater than equal to 0. This
So
is, yeah,
x is greater than or equal to 4.
perfect. And then if you want to spruce it up a little bit, you can do your set notation. X is an element of 4 to infinity. So yeah, pretty much all you're ever doing is identifying, okay, I have that function type, it is an even root, therefore I'll look at my lookup sheet, or if you've got it memorized, of course, you do it that way. Yeah, precisely that. Let's change it up ever so slightly. What if I now have f of x equals square root of x squared minus 4? Something's changed, but not much. How are we going to find the maximal domain of this thing? Not a typical graph you'll be required to sketch yourself, at least not the full thing. But the first thing to identify is what general type of thing is it? And this is still going to be an even root, right? Is the square root of a function. So that's going to be our dot point 0.8. So once again, the exact same rule is what's required. X squared take 4 greater than 0. Oh, sorry, greater than or equal to 0. Now, one of the challenges of this, a common pitfall, is students will be tempted to solve this like a linear inequality. X greater than or equal to plus minus 2. And suddenly you run into like a bit of a weirdness here, which is to say, well, okay, x greater than or equal to positive 2 and negative 2. Well, then wouldn't that just simplify to just negative 2? This is possible to do in this way. You just have to be really, really sure with what you're doing. The way to do it properly. Oh yeah, you can.
For this, okay, this one's because of x squared, it can't. So if you put a negative number, it will be the same as putting the positive number in.
Yep.
So yeah, so x won't be equal to 2 because 2 and negative 2. So because 2 squared minus 4, that's 0. Okay, no, that's still viable.
Yeah, it's going to be viable. So you found the breakpoint, which is good.
It can't be. Okay, so I guess it can't be between 2 and negative 2.
Can't be between 2 and negative 2. Yes, can't be between. And I think, yeah, Haley's also got that in the chat. So yes, you can do it this way where you're just trying to, like, in your mind, trying to figure out, okay, well, x greater than or equal to 4. I need numbers that are on the outside of that, right? Anything bigger than 2 or less than negative 2. Which is perfectly fine. If you want to do it that way, just the basic rule is split it out in like a double inequality. It gets a bit messy though. So yes, you can do it the way you've done it, but also just as easy as to sketch what you've done, right? You've got everything on the same side. X squared take 4 takes 0 effort to sketch. It's just shifted down by 4. And then even just looking, right, where is it greater than 0? Well, it's outside of this and it's outside of this because you have positive y values. So as long as you know what this and that are, that's the other way of doing it, a graphical way, so you've got something to look at as well. And that approach will help you for, if I said like natural log minus 4, it's going to be a lot harder to do something like natural log minus 4 and picture that than it is for a quadratic. So it's just a nice little general purpose way of doing it. But sweet, I'm glad that we're getting even the more complicated ones sorted. So if we're getting those kinds of complications sorted, maybe the next thing I'll make up my own. I'll put in a few. Yeah, actually, let me look at my list. What kind of graphs can I use here? Actually, I can't do two. Let's do something like this. 1 over x squared. I've got to actually pick one that can work, is the thing. I've got a quadratic that I can use. Let's just make one. X squared plus 2x. No, it's going to be minus 2x. I think this will work. X squared minus 2x minus 1. And even if it doesn't work, we'll still get a reasonable answer. So, maximal domain of this. What's the issue that we're worried about? Maybe I should put this on my little list of things. It's not technically on the list, although we do go into detail when you do look at the possibilities. I'll let you guys have a little bit of a think for now. Okay. So the main issue with this kind of function is any possibility of a divide by zero. Right? Whenever you have a fraction symbol or a division symbol, that's where you've now got the possibility of dividing by zero. So maybe I should put that as like a dot point 10 on this, which is any division is just excluding divide by zeros. So if we're worried about where divide by zeros occur, well, let's try and figure out where they occur, if they occur. So set it equal to 0, the whole denominator, whatever that is, and we try to solve
This one doesn't look to be divisible by 0. I mean, we can't use no. We have. Wait, no. Sorry. So I think I was using the split the middle term method. You
Yeah,
can't do it with that. So I guess we can try with the quadratic method. Quadratic formula.
What were you trying before, sorry?
The splitting the middle term.
Splitting the middle term. Oh, yeah, shit, I've just realized. So I tried to make a factorizer, but it didn't come out to be. Hang on, let me just quickly check the discriminant, see if it does have solutions. Pretty sure it should. So b squared, so 2 squared is going to be 4 minus 4ac. Yeah, okay, it's going to have solutions then. So that's just 4 plus 4 for 8. So as far as quadratic formula goes, x equals negative b, so that's just going to be positive 2, plus minus square root of discriminant over 2a, so 2. X equals 1 plus minus root 8 over 2. So at least it has solutions, it's just not nice ones. Now obviously you can go ahead and refactor that root, or what do they call it again? Simplifying the surd. So you'd split that out into its factors of like root 4 bracket 2, and then finally take that 4 out to root 2, and then just backfill the rest. So yeah, x does have those solutions where it goes to 0, so when it comes to giving our maximal domain, what do we actually do with that information now?
X cannot be those values.
That's exactly right. Yeah, x is not an element of those. So there's a couple ways you could do that. You could do x is not an element of, you probably just use your curly braces here. So you do 1 plus minus 2 root 2 on 2. Or you could do x is an element of real excluding exactly that. Very similar amount of effort there. This is going to be more common to most people because using a not an element is a bit weirder. But yeah, that's pretty much it. So those are the main things to watch out for. You've got each individual graph with its own little unique situations, as well as the possibilities of just generically dividing by zero. Shall we practice any more questions like this, or should we move on to the what is it? The apps of integration. One more? Yeah, let's do it. Where did it go? Bugger. I accidentally closed it. Let me pull that up. Wow, it's really far gone. Jeez. How far did I click? Here we go. Okay, what's the weirdest one that we can do? Yeah, they don't get too strange. Maybe we'll do something like this. So we'll do y equals, let's do x over, let's do x over this. X over negative root 16 minus x squared. That'll make it a bit more complicated. How are we going to do this one? It's a function made up of different function types in there. You've got a kind of linear on the top, and you've got a root-ish thing on the bottom.
Would the square root have to be greater than 0?
Yep, greater than.
But if it was equal to 0, then it would be x divided by 0, which is undefined.
Yeah, so you've gone a step ahead and included two separate things, which is naturally the square root can equal 0, but if it did, no negative is going to save it from being a divide by 0 error. So yeah, you're combining two separate things in one, which is really good. You're able to see that ahead of time. So yeah, we can slightly modify this to say, okay, now negative root 16 take x squared can only be greater than, not equal to 0. It's fine if you want to do the greater than and including 0 and then kill it later on. I don't think it'll really change your solution set at the end much anyway, because you'll kind of have all this working out as is. Now, this one's going to be a bit more of a challenge because this is not naturally a kind of graph we sketch. I believe it's a type of semicircle. So, how might we try and do this kind of graph? Or this kind of inequality, rather.
We get rid of the negative and flip the sign.
Yeah,
inequality.
So that's a nice start, actually. We can make it slightly simpler by flipping out inequality. So now we're looking for less than 0. Sure.
We can take the square root to the other side.
That's where things get a bit stranger, because just like with the oh, actually, is this going to break it? Square rooting definitely breaks it because you get a plus minus. Squaring, not so much. Is that going to do anything weird? I think it might. Let's try anyway. Let's see. Because my worry is when you remove the square root, suddenly you're no longer constrained by making sure this inside is greater than or equal to 0. This is also a weird one as well because we're looking at this positive root somehow trying to get a negative number.
I think we can do this separately, so we can find the. Actually, wait, no.
Yeah, it's a weird one. I did kind of create
Yeah.
this, so let's be real, it might not have a proper solution because I made this one up. So let's think about what the actual think about
We
what
work inside out, so
Mhm.
we can pursue the square root. So that has to be greater than or equal to 0.
So yeah, that inside for this to be valid at all needs to be greater than or equal to 0. Yeah. You can solve this. Yeah, that's fine. We've done a quadratic like this before. That'll tell you where it's valid. I'll also just mention when it comes to roots, what doesn't even matter what's on the inside of this. What can come out of this root as far as a general range, given that the fact that there's no negative sign on this? Or even if you look a step back, what can come out of this, given that there's a negative sign on that?
The square root of anything, the square root of nothing is less than 0. Wait, am I? Wait,
I think you're on the right track, which is to say there's actually nothing that'll really that'll meet this inequality.
Yeah.
Because this was all valid, right? If it's a negative root, there's nothing that'll happen in here that will flip it to being a positive number, because whatever you're doing in here is going to be positive by nature and then made negative, or the other way around, right? Whatever's in here is positive is going to remain positive. So that is to say that when you have a function like this, you may come across the case where, hey, it's actually just not valid at all. This graph does not have at least have that restriction. So if we walk it back to what we were trying to do in the beginning, which is to say, okay, maximal domain, we need this thing to be, so the root itself, the inside of the root, needs to be greater than 0. That's the only thing that mattered. The actual equaling 0 of it itself, that could still happen. This could still equal 0 because it's shifted up and pointing down. So I probably made it a bit more complicated than you'll get. But yeah, essentially, the only real thing that's going to be breaking this is making sure that this part is defined. Because as long as this is defined, then we can start looking at the outer parts of the function of like, okay, when does it go to 0? So let's give that a shot, which was just this bit here, right? We had, so this is going to be x squared less than equal to 16, which is going to be between plus minus 4. So if we do our sketch, 16 up, 4 and minus 4. What we're trying to do here, we want it to be positive. So it's always going to be between plus minus 4, non-inclusive of that, because we don't want it to equal 0 on the bottom. So it was a bit of a red herring to go down the root path and make the whole thing try to be valid. It was more about the inside. Divide by 0 is going to be handled by excluding those. And this x doesn't actually do a whole lot. There's no real number you can put there that'll break x. That's just a basic linear, y equals x. So putting it all together, the only restriction here is going to be cannot be between negative 4 and 4.
Yeah, I think you've reverse engineered the hand graph.
versus infinity to
I've
10.
just
Yeah, basically.
yeah,
It's
I've just crafted on this one.
Oh wait, does it actually come out to be a tan?
Yeah, it looks like a tan.
Oh, that's sick. Now I want to see it.
Yeah,
Let's have a look.
I posted it on the
Oh, you posted it?
chat.
Yeah, sick.
Yeah.
Oh yeah, it's got tannish behavior. You can see it goes undefined at the 4 and -4. Actually, I can't see the other one.
I
Does that
didn't.
mean... No, it's
I've
in
only marked one.
Yeah, I only marked that one. Okay. So you have to manually mark it to show up. Yeah, got it.
Yeah.
Sweet. Oh, that's kind of cool. So you get like a partial tan in there. That's kind of funny. But yeah, so all that to show basically try to keep it as simple as possible. Think about the individual restrictions on each of the graphs themselves. The main issue that we came across on this one was probably, I think we were focusing too much on where does this go to 0, the whole thing, rather than, okay, well, let's just make sure the root is valid to begin with. Because we did a bit of a combining of the can't go to 0 but has to be valid. Again, these are tough things, right? You've got 9 different options, technically 10 when you consider just basic division. So knowing what's what is why I've got the whole individual examples as well as how you handle the combinations themselves. Cool. All right. That should about do it for these kinds of questions. We've still got some time to run over the applications of integration. Let's see. Yeah, we should probably do that. Cool. So I believe some of you weren't here for the initial run through of this, so let's do it basically from the top. Don't have a whole lot of time for all of it. I would say the one that'll come up most, or at least give you the most marks, is going to be this area bound between curves, that whole thing. This does come up a lot, but only as like 1 mark on a multi-choice. So we'll prioritize the ones that give you a lot more marks. These are much more involved. And again, I've got video recordings and lesson recordings of this stuff already, so if we need to revise it again in full detail, just let me know. More than happy to do it in more detail. But okay, area bound between 2 curves. So definite integrals by themselves will typically do the area under 1 curve, whatever curve you put in the definite integral itself, and it'll basically give you the area direct from the curve to the x-axis, whether it's above or below. Area bound between 2 curves is going to leverage our use of definite integrals in a kind of unique, creative way. So, very common exam question. In fact, I literally just reproduced it from one of the exam questions exactly as it was, just color it up a bit. Find the area bound between these 2 functions. Step 1, we need to figure out what that actually means. What does bound area actually mean? Bound area just means that the curves create a complete shape around something. So in that middle bit, in that box I just drew, we can see the blue and the red create a full shape. No full shape is completed out here, there, nothing, right? There's no fully bound shape around it. They just shoot off to infinities out there. So when it's saying bound area, it's referring to specifically where the shape is closed. Next, you want to identify how far horizontally, or basically the domain, that area spans. The vast majority of cases, you're going to be finding the endpoints of the intersection points of the functions. So we all know how to solve intersection between functions. We've done it since linear, right? Linear equals linear, or in this case, we've got quadratic equals linear. Whenever the 2 functions are equal to each other, you can find the intersection points between them. This was a tech active one, so I'll just cast it out there. That's going to give us our interval that we'll be using for our definite integral. From there, we need to figure out which function is on top and which is on bottom. This is a very easy endeavor. Look at what is physically on top of the other one. The blue line is above the red line for that entire duration. So the blue will be considered the top, the red will be considered the bottom. Why does that matter? Well, if we think about the definite integrals of each of those functions individually, Definite integral of the blue line gives you all that blue area. Definite integral of the red line gives you all that red area. What we'll notice is that if we compare the two, the only part missing is the bit in the middle. So if we do some simple area subtraction, starting with a big area and subtracting all of this outside bit, you get whatever's on the inside. Or in other words, this was the top one, subtracting the bottom one. So that's why when we do our definite integral, we do it over that domain that was suggested, but you do it in the order of top take bottom, which in this case is going to be the blue g of x minus the red f of x. Knowing how to do that by hand, sure, it is just a definite integral at the end of the day. You can do it by hand perfectly fine. You'd probably not want to do this one though. Shoving in x equals 18 and x equals minus 12 into that, squaring those, yeah, no thanks. So lucky it was tech active. Conceptually speaking, how are we going with that? Any clarifications at all? Sweet. So the reason I'm teaching it and showing you like the geometry of how it works, one is because that's nice to know, right? It's good to know fundamentals over everything else. But two is because it will help you with more complicated crossovers, because essentially all you're ever trying to do is figure out at each stage what's on top and what's on bottom. It turns out to be the case that this is generalizable across all possible curves in all possible configurations. And what I mean by like configurations is physically where they're located on the graph. Like for instance, this is located in the top right quadrant, whereas other graphs could be bottom also, like here, right? It goes underneath. The great news about this is that we don't even have to care whether it's above or below the x-axis like we did before. If you remember from when we were doing our definite integrals last time, signed area, or whatever comes out of the definite integral, is positive above and negative below. But when we do bound area, total area, any of those keywords, we want to make sure everything is positive. What I'm saying is that you don't actually have to care when they are, when we have this sort of thing, when they are bound between two curves, you don't care whether it's above or below because it works itself out. What's considered on top and what's considered on bottom will flip how the arithmetic works in your favor every single time. So, you know, if the curve was under here, for instance, you'd have this bit would be considered negative. But because you're now below the x-axis, the bit that's on top is less dominant than the bit that's on bottom. So it reverses itself right back to being where it needs to be. I'll stop trying to explain that in more detail. Just sort of basically put, you don't have to worry about where the functions are. You just need to worry about where they cross over and what's top, take, bottom. You can explore the geometry of those things if you like to get a better bit of detail from it. But for now, yeah, essentially, if you have these crossovers, what do you do there? Well, now you're just going to do it in more than one stage, because what's top and what's bottom is changing. So figure out where do they change. As for how this shape came to be, right, where's this random black line of x equals 1, right? Why is this bound when I said before that those are never going to meet? Why am I cutting it off here? There's a few more things that can be introduced in the wording of the question itself. So this one says, find the area bound between the inverse and the f of x and the line x equals 1. So not only will they introduce functions, but sometimes they'll also introduce a nice cutoff. This could be, in the case of x equals 1, a cutoff on like the horizontal bit, but it could also be a ceiling of the function itself, or maybe a floor, which would be like a y equals thing. Like for instance, we came across one earlier where this bit had a floor of y equals -1/2. Right, so you can have these additional lines in there as well that aren't necessarily, I mean, that one's a function. X equals is more of a relation. Point being, you can have lines associated with it as well. So, as always, get your sketch if you're not provided one. In this case, we had to make up our own because it was fully worded like that. Identifying the bound area is going to be a matter of, again, seeing where are the shapes created. That's a clear shape, and then this one is made up of 3 lines. Got the blue, the red, and the black to finish it up. Only difference here is going to be what's top and what's bottom. I said before, we need to find that crossover point, and we've done that before as well. How do we find where the functions are intersecting? Well, we make them equal to each other. This particular circumstance has an even nicer way of actually finding that crossover point. Anyone want to suggest a nice and quick way of getting that crossover point? Something unique to this particular scenario, where these functions meet. You use it pretty much all the time in Tech Active. Got something to do with that F inverse.
Equated to the y plus x.
Equating it to y equals x. That's it. That's another way of doing
multiply it.
Yeah, so basically, multiply by 2. How do you mean? Oh yeah, double this. You're right, because that's if you're going for like area stuff. If you do your top take bottom with the y equals x, you'd get like this top half and then double it. Yeah. I was more so talking about just finding this crossover itself. But yeah, what you've said is perfectly fine. The whole thing about why you can equate it to y equals x is because if we look at what the inverse actually is, geometrically speaking, it is a reflection about the line y equals x, this dotted red line. And because you're reflecting in that mirror, any intersection between a function and its inverse will only ever occur on that dotted line y equals x. So if these are stupid, nasty functions that sometimes in Tech Active your CAS can't even comprehend or create when you do your regular inverse equation creating, you don't actually need this one. You can just do function that's easier to do equals x, and then CAS solve that instead. Much nicer. But this one obviously was easy enough to just, you just can do this. These aren't too bad. But if they were harder, you'd definitely consider doing that instead. Identifying the crossover point is important because now essentially we're going to split up our domain in 2 parts. We've now got this 0 to a half bit, and we've got this half to 1 bit. 0 to a half, red is on top of blue. So we do, red, yeah, okay, I've done the color coding a bit weirdly. Let's try reword that. F is above F inverse. So red above blue, F is above F inverse, F is above F inverse for that 0 to a half. Then we do a separate definite integral, half to 1, where the opposite is true. Both of these, you plug in your CAS, or, God forbid, if you have to do tech-free. Fair enough. Yeah, Taha?
Will these normally be Tech Active? Like most of the integration stuff?
No, not most of the integration stuff. Most of the hardest integration stuff, yes, it'll definitely be Tech Active. Bound area itself is pretty doable tech-free. These were pretty nasty big numbers. I'll see if I can pull up an exam that has it. I'm just going to kind of shoot in the dark and see if I can find one, but I'm fairly certain questions like this, to this level of these area bound between 2 curves, is pretty common to see. Let me see, I'm going to pull up a random one. Hopefully it shows up. Yeah, already you can see bound area. This is an exam 1 right here. So you got, I'm assuming, 2 separate exponentials trying to find that bound area. Well, F is above G. So you do top take bottom from 0 to 2. That's why there's only 1 mark. You can very quickly see what that's going to be. Top, bottom, and this x equals 2 is going to be your cutoff there. then now this function's obviously a bit complicated. I'm assuming something in the previous part's going to help you out with actually evaluating that. But yeah, this sort of stuff does show up tech-free. Fair enough. They're definitely worth playing with. And you can see how many marks it's worth, right? 1 to 3, because, well, 1 to get the actual equation itself, and then 3 to basically evaluate it. Is it doing it? There's even another one over here, actually. Part D of the next thing. You got all this bound area. Line 1, line 2, and 2 decaying exponentials. Decaying circular functions, sorry. So what are we going to do here, right? This one's even weirder than before. Couple of ways you could do this, but we're kind of getting a bit ahead of ourselves, I think. Just broadly speaking, you could imagine sort of finding total area, where you do your line 1 and line 2, just trying to find the big triangle worth of area, and maybe just subtract the parts in the middle. Because if you just try to do your top and bottom approach, well, for this part, you've got top of bold, then the non-bold, then bold again, and also, well, I guess you could just double it afterwards. But point being, you'd have to do 3 integrals for that. Whereas finding, no, I think it's still going to be 3 integrals either way. But one might be easier than the other. Point is, there's a couple of different ways you could do it. And thinking about things in terms of the geometry and how much area you're creating and subtracting is nice for handling these kinds of questions. This was my exam, 2018. I had to deal with this shit. And I can almost certainly guarantee you I got it wrong. But I won't do that now, if only. Anyway, that's about it from me. If you have any further questions, feel free to let me know. Happy to stick around for a little bit. Otherwise, thanks for coming.
Thank you.
No worries.
Thanks. Have a good day.
You too. Thank you.